Welcome everyone to today's seminar. So our speaker is John Evans. He's associate professor at University of Colorado Boulder. He's interested in computational fluid dynamics, structural dynamics, computational acoustics, electromagnetics. He's done quite a lot of work in immersed techniques and isogeometric analysis. And I guess today's presentation is related to his work on immersed and isogeometric analysis. And welcome, and thank you for accepting our invitation to present. So, yes. The floor is yours.
Thank you so much. Thank you for the kind invitation. It's wonderful to virtually be here today. And as William mentioned today, I'm going to talk about a topic that's really the intersection of many of my research interests, in particular in immersed finite element methods and isogeometric methods. And the topic of my talk is particularly inspired by the difficulty associated with implementing these methods, and in particular, if we want to retrofit an existing classical finite element code into an immersed finite element code, this typically takes a ton of effort, and I'll inspire why that is the case a little bit later. And this really drove us to introduce this new immersed paradigm that we call interpolation-based immersed finite element and isogeometric analysis. So without further ado, I should really call out those that did the majority of the work. So when this project started, it was an NSF funded project a few years ago, really was a collaboration between two teams. Our team at the University of Colorado Boulder, which involved myself and Kurt Maute, and our co-advised student at the time, Nils Wunsch, and a team at the University of California, San Diego, led by Professor David Kamensky at that time. And the majority of the work done at the UCSD side was done by Jennifer Fromm, but PhD students Xiang and Zhao also contributed to that effort. And the idea is that the CU Boulder team really developed the pre-processing tools, and I'll talk about what that means here in a little bit. And the UCSD team really was in charge of retrofitting existing finite element code, in this particular case, the popular FEniCS platform, into an immersed code. So just want to highlight again, Nils and Jennifer did the majority of the work, and David, a couple of years ago, decided that he was done with academia and wanted to make, I guess, real money and industry, and enjoyed core form. So David left the project and J.S. Chen at that time became the UCSD PI and led us to investigate some of these ideas in the context of meshless methods, which I'll finish my talk here today by discussing. And then a couple of years ago as well, an undergraduate student who then continued on with his master's here, Ryan Caputo, joined the team, and in particular, he investigated the use of so-called curved foreground meshes, and I'll describe what that means here in a minute, as part of his undergraduate research and into his master's thesis. Next slide, I always have to do this, giving a talk either in person or virtually. Come visit us in Boulder. So I'm at CU Boulder, and in particular, I'm in the Ann and H.J. Smead Department of Smead Aerospace Engineering Sciences. We're on the Front Range in Colorado, and aerospace in particular moved into a new building in 2019, and we all know what happened in late 2019 and early 2020. So we all moved out of this building and moved back in a couple of years later, so the building really feels new, even though it's 6 years old. So it's been wonderful to work here, and we love having visitors. So if you have any reason to visit us at CU Boulder, please do. Okay, so with that precursory material behind us, let me talk about the motivation behind interpolation-based analysis. So to begin, as you all know, and this is an image that my old PhD advisor Tom Hughes would show all of the time. Classical finite element analysis requires the generation of a high quality body fitted finite element mesh. In very complex applications, for instance, like analyzing a submarine, this can require a ton of time. There was a DART study performed in the early 2000s by San Diego National Laboratories that actually identified up to 80% of the time required in design through analysis cycle really was dedicated to taking a design, a model into an analysis model. Now, this is, but by some measures, a rather pessimistic view. But there's many reasons as well why classical finite element analysis sometimes can be a bit challenging. And I should note that generating a high quality, emphasis on high quality, body fitted mesh is particularly difficult. And this is the case for geometrically complex, multi-material, multi-physics problems, such as shown here, a heat exchanger. This was actually a geometry courtesy of Interpolation, which has really been investigating topology optimization approaches as of late and looking at really interesting designs. You can think of fiber composite structures where you have a fiber composite layout in a matrix, or biological structures such as a bone. Now, early on in my life, I started in the field of isogeometric analysis, and the big promise of isogeometric analysis is that it directly employs the basis employed in CAD, computer-aided design, for CAE, computer-aided engineering, and thus bypasses the need for the generation of a high-quality body-fitted finite element mesh. However, there is a caveat here. Isogeometric analysis, at least in its original form, requires an explicit parameterization of the geometric domain. And thus it cannot actually be applied to the most common CAD geometries described by NURBS. These are trimmed CAD geometries where you basically have a bunch of NURBS patches, and then you basically apply some scissors to those patches and try to tie those objects together. And it turns out that doing so is actually a really nasty exercise due to the fact that the intersection of two bicubic surfaces is actually an algebraic curve of degree 324 in physical space, or 108 in the parametric space of either of those two NURBS patches that are coming together. So this is a really nasty unsolved problem in geometry. And the problem is even worse in 3D. And this is due to the fact that in CAD, especially described using B-reps or boundary representations, we describe volumes by their bounding surfaces, not by parameterizing the volumes instead. So my old student Luke Engvall used to joke that SolidWorks really should be called Surface Works as a result. So you need to actually do some volume parameterization or meshing anyways when working with a B-rep if you actually need to conduct a volumetric finite element analysis or isogeometric analysis, what have you, as is required for analyzing fluid flow, acoustics, electromagnetics, deformation of a solid structure, etc. And immersed finite element and isogeometric analysis is another approach that bypasses the need for the generation of a high-quality body-fitted finite element mesh. And the idea here is that you instead define basis functions in a non-body-fitted background mesh that basically encloses the geometry of interest. And what this means is that we can define the basis functions that are used to represent solution fields such as displacement for structural mechanics problems, velocity and pressure for incompressible flow problem on this nice, simple background mesh. Right. And then the idea is that you'll perform integration over the actual physical domain and utilize techniques such as Nitsche's method, penalty methods, Lagrange multiplier methods for enforcement of boundary conditions. Now, immersed finite element analysis is also very powerful because it can be applied to problems that are thought of as out of reach Now, out of reach here is probably a bit of an exaggeration, but it's very hard to do using classical finite analysis, isogeometric analysis, such as problems exhibiting a change in domain topology. So an example of this, as shown in the video here, is when you've got a heart valve, right, that you're trying to model the deformation of due to blood flow moving past the valve. And when the valve is closed, and here it doesn't fully close in this video here, but you can imagine if the valve is fully closed, the fluidic domain actually is topologically equivalent to two cubes, right? Because you basically have these two cubes separated by this membrane or this valve. But when the valve is open, then it becomes topologically equivalent to one cube, because now you can actually walk from one side of the valve to the other. And if you try to treat this problem with classical finite element analysis in a paradigm such as an arbitrary Lagrangian Eulerian approach, where you actually move the fluidic mesh as the valve and potentially the blood vessels around that are moving, what you find is you often collapse many of your elements down to zero volume, and this can lead to blow up of code. And another example where you have a change in domain topology is when you're trying to actually model, say, blood cells moving through a capillary. And in this case, the fluidic domain topology changes as blood cells enter and exit the domain. So this is an image taken from a work from Hugo Casquero on the divergence conforming immersed boundary method, where he developed this immersed technique based on combination of isogeometric analysis, so-called divergence conforming discretizations, which I investigated my own PhD work, so super exciting to me, but was able to handle problems such as this, where you actually have blood cells moving through a capillary. And what motivated us for this particular project was level set topology optimization. An immersed finite analysis is ideal for this application, as the geometric domain does not need to be parameterized or remeshed at every design iteration, with the caveat of you may need a mesh for integration, right? And we actually take advantage of that fact in interpolation-based analysis. But the bright side there is if you're developing a body-fitted mesh for integration, the quality constraints that you need to have a good basis no longer apply, right? So you can actually develop pretty poor quality meshes and still be okay. Now, the primary challenge of immersed finite element analysis is implementation. And it's challenging and time-consuming task even for domain experts. And the primary challenge is numerical integration over cut cells. So in this image here, we can imagine that the physical domain here is depicted in gray, right? And we denote this as omega. The boundary of the domain is denoted as gamma. And we're using a background mesh here, which is the boundaries of the mesh are denoted in this light gray lines as seen here. And if we have background cells living fully inside the domain, we can use, say, standard Gauss quadrature rules to perform integration. But for these cells that are cut by the boundary of the domain, and what you see is like an example here, where the part inside the domain is denoted in gray and the part outside of the domain is denoted in yellow, we can't use standard Gauss quadrature. And we need to come up with specialized quadrature rules for every single one of these cut cells. And as you might imagine, there's been many different rules that have been developed, many different strategies, including, for instance, quadrature over a body-fitted tessellation. And you can imagine this tessellation could be either consisting of straight-sided elements or curved elements. And this tessellation is just used for integration in this purpose. You could use quadrature over a quadtree or octree mesh, which is commonly employed in the finite cell method. Or another technique, for instance, my research group has investigated using Green's theorem to devise quadrature rules by transforming volume integrals to surface integrals and surface integrals to line integrals, and line integrals to point evaluations. Now, with all of these, though, you need to actually have specialized quadrature rules, and not just that, but specialized quadrature rules for every single cut cell. And with many classical finite element codes, implementing these quadrature rules really requires a reworking of the underlying code. So we asked ourselves, is there another approach that we can take with Immersed? And this led to the development of the so-called EXHUM project, which stands for Extraction for High Order Finite Element Methods. And the purpose of this project is to ease the burden of implementing an immersed finite element code. And in particular, what it enables is one, to transform classical finite element codes into immersed finite element codes with minimal implementation effort. And the key technology underlying this project is the concept of interpolation-based immersed finite element analysis, and that's what I want to talk about next. That leads to part 2. So diving right in, what we're going to do now is leverage the Poisson equation as a model PDE for exposition. So we're going to consider this potato domain omega here, right? And we're going to consider the problem, the Dirichlet problem, find the solution U such that minus the Laplacian of U is equal to F, where F is prescribed inside the domain, and U will be equal to a prescribed function G along the boundary of the domain. And as all of us here know, right, finite elements methods start from a weak form, and for this problem, the weak form is find U in the set of functions in H1, right, so the set of square integral functions of square integral first partial derivatives, such that U is equal to G in the sense of trace along the boundary of the domain. We can write this as find U in the space of functions H1 that are 0 along the boundary of the domain, plus a lifting of G inside the domain, such that for all weighting or test functions V in H1 naught, we must satisfy integral over the domain of gradient of U dot gradient of V is equal to integral of the domain of F times V. So that's basically the first couple of days of finite element analysis 101. And here we just basically took this PDE multiplied by a weighting function and integrated by parts. And the discrete problem that we utilize for immersed analysis much of the time looks as follows. If we use so-called Nitsche's method for weak enforcement of Dirichlet boundary conditions. So what we do is we augment this with a so-called consistency term that results from integration by parts, a symmetry or anti-symmetry term that acts to make the stiffness matrix either symmetric or the contribution induced anti-symmetric, plus a penalty term that restores coercivity in the case of a symmetric Nitsche method. And we throw an H on everything, in particular on our space of discrete trial solutions and test functions, which here are equivalent, which is saying that we are going to represent the solution field basically in terms of a finite sum of coefficients times basis functions. And with quadrature-based immersed methods, which are the most common, we define the VH, right, with respect to a background mesh. We can then use standard element Gauss quadrature on cells contained inside the domain. And the challenge is already articulated as integrating accurately over the intersections of the domain with cut cells. And one solution that I highlighted was tessellating these mesh cell intersections with quadrature elements, forming a foreground mesh. And then over each of these subcells, we can use standard Gauss quadrature. So then if you take a look at what this looks like in terms of implementation, what you see now we have to do is we have to perform integration over each of those foreground cells, each of those integration elements, and then we need to sum. Now, the implementation problem now is that the quadrature here is defined on the foreground mesh, but the basis functions are defined on the background mesh, right? But standard finite element data structures and assembly algorithms just work with one mesh, right? So we can't utilize these standard finite element method data structures and assembly algorithms, which led us to instead turn to these interpolation-based immersed methods. And the primary want behind the design of these methods is basis functions that are used for assembly defined on the same mesh as the quadrature rule. The basis functions before are defined on the background, and the quadrature is defined on the foreground. And our approach really is quite simple, and it's defined as follows. We first just define a nodal basis on the foreground mesh. And this foreground mesh can be of very poor quality, but we can still define a Lagrange basis on it. And then what we're going to do is we're going to take our background basis functions, and we're going to interpolate these background basis functions into the foreground space. Or in other words, we're going to take each of our background basis functions, which we'll denote as Ni, and we'll interpolate them, resulting in these Ni hats, which you can think of as being sum over the nodal basis on the foreground mesh. And then we're going to just take our background basis, we're going to evaluate those at the foreground nodes, and then multiply by the corresponding foreground basis functions. So we're approximating the background basis functions with these foreground basis functions. And then we'll use the span of the interpolated background basis as our solution space. And it turns out that this ends up being equivalent to a quadrature-based method if the foreground mesh is fitted to the background mesh. So that means that each foreground cell lies within a unique background cell, and the foreground basis can exactly represent all of the monomials in the background basis functions. However, we actually get possible approximations and new numerical methods. For instance, we can actually have a reduced polynomial degree of the foreground basis. We can say, hey, let's not worry about trying to represent each of the background basis functions exactly. And this allows us to use, for instance, a reduced quadrature rule. And this can then in turn lead to a more efficient assembly. Moreover, what we can actually utilize is a background unfitted foreground mesh. That is, we can actually use foreground cells that actually can straddle multiple background cells. This is not the case with quadrature-based immersed methods, because you actually lose accuracy because you need to actually have enough accuracy of your quadrature rule to maintain accuracy in your final solution. So this gives us more flexibility in mesh generation. And here I should note this is generation of the foreground mesh, so it doesn't need to be particularly high quality. So to present a picture to describe this a little bit more clearly, let's consider the case of a domain where we've got a square with a diamond cut out of it. All right, so the domain here is depicted in red. And then we're going to use a background basis of quadratic or biquadratic B-splines, and we'll define this background mesh here in black. And I'm just going to take one particular C1 quadratic B-spline. And now what we can do is we can create a foreground mesh, right, that is body fitted, for instance, by creating a triangulation such that each of the triangles lies within a unique background cell. So this gives us a so-called background fitted foreground mesh. And then we can interpolate onto either a linear or quadratic Lagrange space defined over this mesh, and we get these two approximations of the background basis function respectively, right? Or we can instead not worry about trying to ensure that each of our foreground cells lies within a unique background cell, and this gives us a background unfitted foreground mesh, new possibilities, and then we can interpolate using either a linear or quadratic Lagrange space, and these are the corresponding approximations that you get for the interpolated basis functions in this case. And you can see in either case, all right, we actually get quite a nice representation with quadratics, even though both of these are not exact. of representations of the original quadratic B-spline basis functions, because this function is actually quadratic in both directions, while these approximations are simply quadratic rather than biquadratic. Now, if you recall, the idea here is to actually allow us to reuse an existing finite element code. So how can we do that? So the matrix notation for the discrete problem we want to solve in this case, using this interpolated background basis, looks as follows. We get a stiffness matrix K times the displacement vector D is equal to a force vector F. We can form K, we can form F, and we want to know D. And the entries of K look like Kij of AH, which is our underlying bilinear form associated with this Poisson problem, with entries n hat j and n hat I for our trial and test lots respectively. So we've just taken our interpolated background basis into that, and our ith entry of F is taking our linear form, defining our right-hand side, and taking as input our ith interpolated background basis. Now, what is easy to assemble over the foreground mesh with an existing finite element code is not this, right? But is instead essentially evaluating our bilinear and linear form for our Lagrange basis defined over our foreground mesh instead, right? That's what a classical finite element code is utilizing. So we can form a matrix A with entries Aij equal to AH of phi j phi I, and a vector B with entries Bi equal to LH of phi I. Now, fortunately, we can represent our interpolated background basis purely in terms, right, of these foreground basis functions phi, which actually in turn means that we can actually represent big K in big F in terms of big A in big B defined here, an appropriate transformation to transform the problem into our interpolated background space rather than the foreground space. And this means that we're just going to multiply pre-multiply A by M transpose and post-multiply by M, and pre-multiply F by M transpose, where Mi here, this extraction matrix, has entries Mij equal to the jth background basis evaluated at the ith foreground node. So all we have to do is evaluate our foreground basis functions at these foreground nodes a priori, and we get a matrix, and then we can form A and B using our classical code, put it together, and we have a matrix system that we can solve. And the only non-standard assumption here is that the existing finite element code can implement AH here and LH here for Nitsche's method, right? Because we now have additional terms versus a finite element code that strongly enforces Dirichlet boundary conditions. We have a consistency term, a symmetry term, and a penalty term. So that's it. And for background fitted foreground meshes and under various technical assumptions, we actually have a best approximation bound. Basically says the best approximation with respect to our interpolated background space satisfies a usual error estimate. So we see that the best approximation error is bounded from above by some constant C that doesn't depend on mesh size, times the background mesh size, H raised to power K hat times the norm of U. And K hat here is the minimum of K and kappa, where K is the polynomial degree of the background space and kappa is the polynomial degree of the foreground space. You can think of this as the minimum degree of polynomial completeness. So it's telling us that we should take, if K is fixed here because we've chosen a given background space, we should choose kappa to be at least K, but no bigger, because otherwise we're not really gaining anything in terms of approximation order. Now, the background space may have some monomials with degree greater than or equal to K, but these don't actually need to be captured in the foreground space for optimal order interpolation error. And numerical results actually indicate that this result is actually quite conservative, and this holds under significantly more general conditions. We've been working to prove more general conditions for which this holds, but that's work in progress. So how does this perform? So here's just a simple example of 2D Poisson with a background fitted foreground mesh. And in these plots here, we're looking at L2 error for linear discretizations and quadratic discretizations versus number of degrees of freedom respectively. And on the right, we're looking at H1 not error or H1 semi-norm error for linear and quadratic. And this is linear and quadratic of the background space. And then we use linear and quadratic as well for the foreground space in this particular case. And in blue here, we have traditional finite analysis performed on the foreground mesh. And then we have the interpolation-based immersed method in purple, and the quadrature-based method in green here. And you can see that we are attaining optimal approximation order for all cases here. And we can see as we raise the degree, we actually aren't losing much with interpolation. Now we expect to actually lose a little bit, right? Because we're not using the original background basis, we're instead interpolating. But this is indicating that we're really not losing much, and we're gaining the ability to implement this approach in a classical finite element code with minimal implementation effort. So little loss for a lot of gain. And then this also extends to 3D, and you can see that in 3D, we actually get that interpolation-based and quadrature-based approaches really collapse onto each other. So here, there's a big gain to be had and for a little loss with moving to interpolation-based. Now, what's remarkable is this approach also works with the background unfitted foreground mesh. And this is outside of our theory, and this is certainly not something that you can utilize with classical quadrature-based immersed methods. If you use this integration mesh with the quadrature-based method, you would not get optimal error convergence whatsoever. So this is a really exciting development that tells us that we can do really wacky things with foreground mesh generation if we so choose. And if our background space is higher order, consists of higher order continuous functions, then we can leverage this to solve higher order PDEs, such as the biharmonic equation. And this inspires us to also leverage interpolation-based immerse to solve said PDEs. But since we're interpolating onto a C0 foreground space, we actually lose C1 continuity in the process. But what we find is we are still able to solve these problems, even though our corresponding discretization is now non-conforming. So that's actually pretty exciting. It means that we can solve, for instance, plate and shell problems, and I'll demonstrate that here a little bit later. And then we can, look at, for instance, nonlinear problems such as fluid flow. For this example, we're going to look at a very simple problem, Taylor-Green vortex with a Reynolds number of 100. And we're going to use equal order elements for the background, project onto the same foreground space, and add VMS stabilization to address advective instabilities, as well as a lack of satisfaction of the INF-SUP condition between our velocity and pressure spaces. So here represents our SUBG stabilization term, SUPG and PSPG stabilization term, our rad-div stabilization term, and then we have some non-standard stabilization terms coming from VMS as well as our terms associated with reinforcement of Dirichlet boundary conditions. And just to show you an example, here's an example of a background mesh with an overlaying foreground mesh. And here we're going to actually use a non-conforming, or sorry, non-background fitted foreground mesh, again, just to show that this can work. And here's our background mesh with the exact solution. and looking at our velocity errors as measured in the L2 norm and H1 norm, and pressure as measured in the H1 norm, we see that we get optimal convergence in all cases with this. And then we can do things such as image-based analysis for composite materials. So here, what we're doing is linear elastic analysis of aluminum particles embedded in epoxy. And what we're given is just the image, micro CT image that's attained. And we can leverage our framework immediately to perform image-based analysis for this application. And on the left is our immersed finite element analysis result, and on the right, our body-fitted result. Here we're plotting von Mises stress, and you can see that according to the eyeball norm, things match. And if you zoom in and take a look at the mesh as well, and you can see that we're really getting the local solution features with this interpolation-based approach, even in this image-based setting. And we can also analyze multiphysics problems such as thermal elasticity. So this is an example, a simple example of heating of a plate with an inclusion. And here are the Young's modulus Poisson ratio for the two different subdomains in this case. And here we got thermal elasticity, and here's our alpha for these cases as well. And you can take a look at comparing interpolation-based and quadrature-based immersed isogeometric analysis with the same background mesh, and you can see that we're nailing the von Mises stress. Then just a last eye candy before I talk a little bit more about transforming classical codes into immersed codes using our software package Exum. What we're going to do is analyze a Kirchhoff-Love example problem. We're actually going to pull on this tab of this shape here. But the shape here actually is going to be first kind of unwrapped into a cylindrical shell. And we're going to tackle this problem using both a background fitted and a background unfitted foreground mesh as seen on the left and right here. And in this movie, you can see the structure deforming as we pull on that tab, and you can see these two different approaches yield qualitatively very similar looking results. And if we compare against a converged value attained using classical body-fitted isogeometric analysis, here we've got a Kirchhoff-Love shell. This is governed by a fourth-order PDE. We actually can't utilize a displacement-only classical finite element code to tackle this problem. We have to turn to mixed instead. We can see that we actually converge quite quickly, both the background unfitted and the background fitted approaches. So that was a quick tour de force of introducing you to interpolation-based analysis and showing you some results for some simple cases. In part 3, what I'd like to talk about quickly is how do we transform classical codes into immersed codes with Exum. So what our new software library Exum does is it creates foreground meshes, extraction operators, that's those M matrices, either element by element or a global matrix M, and connectivity arrays outside of the confines of any particular finite element code. And the vision here is that Exum reads in the background discretization and geometry representation, and then it spits out these extraction data structures that are needed for interpolation-based immersed finite element analysis. And then you can feed this into a retrofitted finite element code that will give you an unfitted finite element solution. And our code base also allows for the generation of an XML VTK file for visualization with ParaView. And as will be demonstrated in the next part of this talk, we've leveraged these extraction data structures to transform the popular open source classical finite element code FEniCS into an interpolation-based immersed finite element code with frankly only a few lines of code. And to create Exum, we leveraged the Morris software library developed by Kurt Maute's group for FEM based level set topology optimization. And underlying Morris is a hierarchical background mesh generator and a geometry engine. So we call these HMR and Gen respectively. And Gen handles level set fields, descriptions of geometries, and hierarchical background mesh generator generates the background meshes to be leveraged within interpolation-based immersed analysis. And what happens, you can imagine, is that this will deliver Gen with the mesh for level set discretization, where now you can imagine trying to refine according to the geometry, and this can be passed back to HMR. And then we have an immersed finite element toolkit XTK that generates the foreground mesh for us, and also computes the extraction operators that are needed for interpolation-based immersed analysis. Now, Morris allows for immersed analysis directly within it, as well as topology optimization. So it actually has a separate finite element module that reads in a background, foreground mesh pair and extraction operators, and it performs actually quadrature-based immersed analysis, and then it links up to an optimization engine that reads in design sensitivities and updates the design respectively. But those two parts are not needed for interpolation-based analysis. So Xoom really focuses on HMR, Gen, and XTK. So XTK output that we need here for interpolation-based analysis really will be these extraction operators and the connectivity arrays that are needed. And the idea here is we define the geometry in Gen, the background mesh and basis using HMR. Therefore, this is really what Xoom is all about. So what can our geometry engine handle? It can handle user-defined level set fields, predefined geometries, 2D, 3D image files, and STL files with closed surface. And in terms of HMR, it can handle both tensor product and locally refined using hierarchical B-spline discretizations. And then HMR then defines the grid for decomposition, and XTK then gives us the foreground mesh that we need for interpolation-based analysis in Exodus format in either global or elemental extraction operators, as I already alluded to. Okay. Again, a whirlwind tour. I'm trying to cover a lot of ground here today. How do we now enable interpolation-based immersed analysis in FEniCS? I know I don't want to speak too much to the FEM crowd about using FEniCS, but my main inspiration for talking about that here today is we should be able to leverage immersed analysis in FEM, interpolation-based analysis, almost as simply as done inside of FEniCS, except for the fact that FEniCS here is really leveraging UFL to kind of do human readable implementation of bilinear forms and the like. So as most of you I think here know, FEniCS is an open source software toolchain that automates the compilation of finite element code and basically allows for easy implementation of variational forms using UFL, this unified form language in Python. And then it generates optimized C++ code to actually generate the stiffness and force vector utilizing classical finite element analysis. And then you can solve then the system to get back the displacement solution, say, in the context of a structural mechanics problem. And the way that interpolation-based immersed analysis works with FEniCS is we first generate a foreground bounded unfitted foreground mesh and extraction operator using our Xoom tools. And then we assemble A and B as described before using the foreground basis phi within FEniCS, right? And then we compute K and F from A and B and the extraction operator as described before. Then we solve KD is equal to F for D. And then we project the solution onto the foreground basis for visualization and analysis. So all we do is we take that displacement vector D, hit it with M transpose, and this now gives us foreground degrees of freedom that we can actually utilize within ParaView. So solving the Poisson problem with classical finite element analysis in FEniCS actually can be described in just a few lines of code. We basically load and mesh and define subdomains first, define a classical finite element function space. Next, here we're defining this to consist of quadratics, and we're using a continuous discretization over a triangular mesh. We then define our variational problem. We define what our bilinear and linear forms are. For instance, we define what our right-hand side force happens to be. We enforce boundary conditions, and we then solve the linear system. With interpolation-based, there's only a couple of additional steps. We first have to load the Xiang module that allows us to do a couple of things, such as pre and post multiply by that extraction operator that I described earlier. You need to enforce boundary conditions weakly with Nietzsche's method, which turns out to be the most amount of code that you need for enforcing interpolation-based immersed analysis, right? So then you transform your matrix system and then solve. So really, it just took a few lines of code to take this classical finite element implementation to an interpolation-based implementation. Okay. And I'm happy to answer more questions regarding that at the end of today's talk. So there's a couple of remaining parts. I first want to conclude the discussion of interpolation-based immersed analysis by discussing current status and future plans. I'll be doing this briefly just due to the sake of time. And then I want to talk about, can we leverage interpolation to implement other sorts of exotic finite element discretizations within a classical finite element code. So the first capability I wanted to highlight is that our code can handle locally refined mixed foreground meshes of tris, quads, in 2D, and tets, hexes in 3D, along with hanging nodes. So this allows us to locally refine our foreground mesh, for instance, along interesting geometry to accurately integrate along interesting geometric boundaries and material interfaces. Our code also supports locally refined background discretizations, and here we leverage so-called hierarchical B-splines. We also leverage this technique called truncation, which actually leads to reduced support size of our underlying basis functions that then actually leads to increased sparsity in our resulting stiffness matrix, either stiffness matrix for a linear problem or a tangent matrix for a nonlinear problem. And it allows us to have a basis that retains partition of unity, which is not the case with the classical hierarchical B-spline basis. To tackle multi-material problems, we enrich. So we use Heaviside enrichment, and one unique aspect of our approach versus other approaches is we actually enrich on a basis function by basis function level. And we found that this is actually particularly important when you've got rather large basis function supports, because you can actually have disconnected material subdomains within the same basis function support in this case. And if you don't enrich on a basis function by basis function level, you can actually get artificial coupling or locking, if you will, that occurs in the resulting system response. And we have support for separate background discretizations for multiphysics problems. So for instance, for the thermoelastic multimaterial problem I talked about before, you may want to use a different background mesh for the displacement field than the temperature field. And our framework allows for this. And one thing that I did not talk about today is that immersed methods do actually exhibit some issues when you've got very small cut cells, in particular when the ratio of the cut cell volume to the background cell volume is particularly small. This results in a very, very high condition number if you're using Nietzsche's method, but it actually can result in a unstable discretization as well. And to combat this issue, we've utilized the notion of a basis extension that was introduced by Eric Berman and co-authors in a CMAIN paper a couple of years ago. I don't want to get into the details here, but the really nice aspect is all of this, all of the craziness associated with this technique is embedded in those extraction operators M. There's nothing else that's required to implement this basis stabilization. So the end user doesn't actually need to modify their analysis code or workflow to include stabilization, right? Since all their code needs to be able to do is handle these extraction operators that now have been modified. So that's really a nice aspect. So planned capabilities. Support for foreground meshes of curved integration elements is currently being implemented within our framework. We've already tested this approach using just a testbed code that we wrote, that undergraduate student Ryan worked on, showing that this approach works quite well. We just don't have it production ready yet. Support for BREPs is currently being implemented. And we're also currently equipping Xiang with the capability to generate and output cut cell quadrature rules if you want to use customized quadrature rules in a quadrature-based immersed method rather than interpolation-based. I only have one over. I know that I got a meeting invite for an hour and a half, but I don't want to take the whole time. But there's a last question of, can interpolation be used to enable other capabilities in FEniCS? And this is something that Jennifer Fromm at UCSD, she's now actually at Lawrence Livermore, investigated to finish her PhD. And what we saw is that we could actually implement mesh-free methods as well inside of FEniCS or any classical finite element code using interpolation. With mesh-free methods, basically the domain is discretized by a point cloud. And at each point, we have a basis function that has its own support. And we use, in particular, the Reproducing Kernel Particle Method, or RKPM method, where we basically have these basis functions that look like this, where you have these correction functions multiplied by your kernel functions to get these functions to look like this. So I don't want to get into all of the details here, but you can imagine if we've got a foreground mesh, we can interpolate these functions as well. And we can refine the foreground mesh to get nicer and nicer approximations of these RKPM shape functions. And you can apply this to multi-material problems with enrichment and local refinement. It performs quite well. And we have a preprint on this that we've submitted. And I also submitted that to the archive, but it's not up yet. So if you want to take a look, feel free to reach out. All right, last thing, useful links. Here are a few links and QR codes to our more software library and FEniCS implementation. We have a couple of papers now, but probably the most useful place to start is this first paper on interpolation-based immersed analysis, and I'll make these slides available to anyone who wants them. And we also had a couple of the collaborators workshops where there's more details given, in this fall 2023 one probably is the most useful. All right, so thank you, and of course thank you to those who provided funding. All right, thanks so much.
Thank you very much, John. Very nice presentation and very informative. I guess people having tons of questions, at least I have. So there is a question in the chat. So your discretization KD equal to F with K equal to M transpose times A times M, and F is equal to M transpose times B, is written basically at the end to solve AX equal to B on the foreground mesh.
Yep.
And then solve M times D equal to X for the solution D on the background mesh, which is really just a projection from one mesh to another. Is that correct?
That's essentially correct, right? It's projecting from the foreground space into the interpolated background space. So we're not actually interpolated onto the background mesh, but instead the interpolation of that background mesh into the foreground space. That's exactly correct.
Thank you for this really interesting talk, John. Can you say something about preconditioning of the resulting system?
Sure. So there's many different strategies that you can employ for preconditioning. With the implementation that we've done in FEniCS, we actually have access to the full-blown K-matrix, so we can, leverage things that actually need access to the full stiffness or tangent matrix for a nonlinear problem. So we actually build preconditioners based on K and not A. Now, if you don't want to fully assemble K, there's other approaches that you could certainly investigate, but we haven't done that at this point. So we looked at standard block Jacobi, block ILU type approaches in this project.
How about some kind of multi-level, multi-grid type, more scalable preconditioners for larger problems in parallel and so on?
Yeah, so I mean, you can use algebraic multi-grid packages, as is, right? Because you have access to the full-blown K-matrix if you form that full thing.
And do you
multi-grid is a different question entirely, where you've got multiple different levels of background. But if you're interpolating onto the same foreground mesh, you can certainly do geometric multi-grid with this approach as well.
And do you expect AMG to work? So that depends on the properties of M, for example. At a minimum, it needs to not reproduce the near null space, so row sum 0, things like that. Row sum 1, sorry.
Sure. So multi-grid for immersed in general is actually a difficult problem. And it has to do with a couple of things. That small cut cell problem that I mentioned rears its ugly head and actually provides all sorts of pains. And this is actually related to the smoother rather than the coarsening of the space. So your standard sort of smoothers that you'd employ for strong enforced approaches don't work. Well, strong enforced body fit approaches really don't work in the immersed setting. And many times as well, you need introduced stabilization, such as the basis extension approach I presented here, or Ghost. And those often don't play nice with multigrid as well. However, there have been developments, but they can be somewhat intrusive.
Thank you.
So let me ask several questions. So you mentioned at the end extension to meshless, mesh-free approaches. Now, if we do this approach for meshless, mesh-free approaches, do we need the stabilization?
So that's something that is a really, really kind of tricky aspect, right? Because, why do you need stabilization? Largely it's due to the quadrature, right? At the end of the day. And with this approach, you don't, right? The fact that you are actually interpolating and then accurately integrating that interpolated basis, right? So that alleviates the standard sort of stabilization that you need with RKPM and other meshless approaches. That said, there are caveats. We've found that there are additional conditions that you need to satisfy between your foreground and foreground mesh and background discretization. There's not really a background mesh with a meshless method, but there are certain things that you need to be careful with in order to have a stable discretization. So we fixed the instability you have with classical meshless methods and introduce potentially new ones that we need to.
Oh, okay.
The preprint gets into more details on that.
Okay. Yeah, I'll be very interested in looking at the preprint. So essentially, you inherit. You can design any C2, C and to C infinity discretization by using the mesh-free, meshless approaches, right?
That's right. And same with kind of isogeometric. Yeah.
Okay. Oh, that's great.
Yeah. Now we don't have theory right now that says that the interpolation-based works, because now you get a non-conforming method. But in the interpolation-based isogeometric setting, everything we've thrown at this has worked. So we're working on how to prove it. Proving it is, as with a lot of non-conforming methods, is proving to be painful. And it turns out it's even more painful in the meshless method setting. But progress is being made. That's a rather recent work. So I expect to see a lot more progress in the coming time.
Oh, that's very nice. It opens a lot of possibilities over there because that's generating this C1 or even C1 actually. Discretization is a quite painful process.
Agreed. I agree.
Any questions from the people here?
Yeah, I got some question.
Yeah, go ahead. Go ahead, Herman.
Hey, John. Great talk first. Also, really cool to see all you guys have done with all this immersed method stuff. I do have a few questions. Since I have some background in this, I was wondering like some issues that I had like a decade ago and see how you guys solved them.
Sure.
So, the process to immerse the mesh, to create the foreground mesh in the background mesh, like let's say if I give you a CAD model, will the process be converting that into like an STL file and then generating a level set out of the STL file and then do the foreground mesh? Or I guess what's the process? That will be my question for like if I give you a CAD model and I want to do this method.
Yeah, so essentially right now, our framework cannot handle B-reps directly, right? Okay. So you have to basically create triangularization, right? An STL file out of that, and then our framework underneath the hood is then working with level sets, just because it works with level sets. The actual, theory doesn't rely on that. That's a limitation of the software package, rather than the underlying theory.
Okay. And what algorithms do you use to generate a level set field from an STL file?
Sure, I would have to point you to another individual there.
Okay.
Yeah, come over. I mean, neighbor. Yeah.
Yeah, I know. I think I'm like a mile away. So.
No, but yeah, no. That is something that I would not be best equipped to address. There's many different ways of doing that process. STL, fortunately, you can think of it as just being a linear, truly kind of linear representation of geometry. Mm-hmm. So you can create an implicit representation, an exact implicit representation much, much more easily than a B-rep. A B-rep, trying to convert a B-rep into immersed, to give you kind of an implicit representation, give you an idea. If you take a bicubic NURBS, right, and you then want to know what the representation of that object along any curve, right, in the parametric space of that object is degree 108. And that's of the implicit representation. So you need to make some approximations if you're going to try to use level sets for representing a B-rep. So if you're going to want to handle a B-rep directly, it is my recommendation, don't go implicit.
Okay. And but your level set field is still linear, or have you guys done any like quadratic when you represent those shapes?
Yeah, so we have the capability for representing shapes other than linear. Nils Wunsch in particular was starting to investigate that. And one big reason we were looking at that was leveraging higher order rules that Xiang had developed that read indirectly level set descriptions without any meshing. So that inspired us to look at there, but that work is unfinished at this point.
Okay. So I guess at this point you will still have the downfalls of using level sets, like being able to represent really sharp corners. Okay.
Yep. You have to use level set fields in that case. Yeah.
But it seems like you can ameliorate that through. It seems like you're doing like mesh refinement along the boundary. So it seems like that probably diminishes the issue a lot. I'm guessing.
Yep. Yeah. No, I think, to be honest, for a B-rep, the best approach would actually be to employ some sort of mesh generator, cell by cell, right? Even calling something like Gmesh, but then basically saying that you can make this mesh as poor quality as you possibly would like.
Okay. And I guess my last question is kind of related to the preconditioning. Do you still have to use like, especially with fluid flow, like things like ghost penalty or what was it called, like the FEM preconditioner? Because I know remember you mentioned like issues where the ratio of cells is small. So you still have to kind of do all that extra stuff?
Yep, and this is where we use this basis stabilization. So this basis stabilization, rather than what happens with ghost penalty essentially is trying to weakly reduce the size of your solution space, right? By penalizing derivatives, right, across spaces. So you can imagine it's trying to smooth things out, it's reducing the space. With this basis stabilization approach instead, we strongly reduce the space. And the way that it essentially works is if you have a bad cut cell, rather than utilizing the original approximation over that cut cell, you look at a neighboring good cell and do a polynomial extension into that cell. But it turns out that whole entire process, with our approach, we can hide all of it in the extraction matrix M. So all of the crazy details that you need for Ghost, etc., in terms of your underlying finite element code go away. Instead, you just bury everything into M. Now, of course, constructing M is the difficult aspect, but that's handled by the preconditioner.
Okay, cool. All right, yeah, that's all I wanted to know. Thank you so much.
Sorry, you asked about preconditioner by the preprocessor. Sorry, yeah.
Okay, thank you.
Yeah, no problem.
Thank you. Thank you, everyone. Any other questions?
I have a question.
Sure.
How sparse is M?
How sparse is M? It's quite sparse. And that's where we actually have two different approaches that you can have for outputting M. One is a global representation, right? Which you can imagine is of size, right? Number of foreground degrees of freedom by number of background degrees of freedom. Or we actually have another approach, which is you output elemental extraction operators, one for each foreground cell. And that second approach is honestly the way that I prefer to think, which is, if you're thinking about it in terms of an element formation and assembly loop, after you formed your elemental tangent or stiffness and force or residual vector, we then transform it into the desired basis and then plop it into the appropriate place. That in that approach, rather than forming big A first and then smacking it with M transpose and M, we are basically taking elemental matrices associated with A and plopping those into the appropriate place in big K.
Yeah. Okay. All right. You may be familiar. I don't know. Oh, not familiar. But we have this finite element decomposition in FEM that everything is pretty much everything we do is viewed from it, and this M is just another part of it. A itself has P transpose APs and G transpose. This transposes on these variational transformations go all the way to the quadrature point.
Right.
So from our perspective, adding another one on top of everything may be almost trivial and may allow a lot of things to happen, to continue to happen on GPUs and so on at the lower level. But one thing that has to be considered here is that the outermost one is where we do all the MPI communications and parallelism.
Right.
And I guess that will have to happen somehow in M for you too. And I don't know how complex that is.
Yeah, and I think it really depends on at what level you use M. If it's going to be an element by element level, or even quadrature point by quadrature point level, you might be able to kind of embed it at a much lower level and not have to worry as much about communication aspects. But the big problem then, of course, is how do you bring M from your preprocessor to your final element code, and how are you storing it? But I'd love to chat more about that.
Yeah, that's very interesting. Thank you.
How do you define the nodal degrees of freedom in the case of levels that when you integrate exactly without background mesh for integration?
Without the foreground mesh for integration? You talk about size work?
Yes.
Yeah, so I will point you to the papers. It's rather complicated, right? So there's not really degrees of freedom, so to speak, but there's a lot of nastiness associated with the algorithm. But once you get it working, it is beautiful, and the math is beautiful for it. But I'm not going to do it justice in a 30-second response. So I'm going to do that thing and get myself off the hook and say, read the paper.
Okay, thank you.